In this video, we're going to go over solutions to a college algebra test that I gave to my students. This test goes over a wide variety of topics in this class. We look at polynomial functions. We look at properties of graphs of polynomial functions. We look at inequalities of polynomial functions, also rational functions. We look at graphing rational functions, properties of their graphs. We look at geometric sequences, arithmetic sequences and series. We look at logarithmic functions. What else do we look at? Conic sections, so ellipses, hyperbolas, partial fractions decompositions. So as you can see, and also solving systems of equations using matrices. So as you can see, there's a wide variety of topics in this exam. So let's go through it. Hopefully this will help you. So the first question on this exam says, look at the graph and answer the following questions. So where is this graph increasing and decreasing? So looking at this graph and looking at it from left to right, we're looking at where it's going up and where it is going down. So from left to right, I notice this first piece is going down. So it's decreasing from negative infinity until we get to the x value of -8. So also it's decreasing here. We're looking at the x values. I'm putting it in an interval notation here, starting at -2 to the x value here of 0. Union, meaning that we're including also the value of x equals 2 down to 5. And the rest looks like it's increasing. So we're going up from left to right. So we're increasing here from -8 to -2, union 0 to 2, union 5 to infinity. And so I'm just kind of coloring in on the x-axis. Those are the values that we're using. And again, this is an interval notation. If we wanted to, we could write this with inequality notation. And my infinity, that should have been an 8. Oh no, that was right, -8. So looking at this, it wanted to know what the range is. When we're looking at the range, we're looking at the y values that we're hitting when we're using this graph. And so first I'm looking at the minimum value. Is there a minimum value, the smallest value that this graph hits? And there is. Looking at this, I see that this value here, when x is -4, is the smallest value my graph hits. And so my y value, we're starting at -4. I'm including it, so I'm putting a bracket there. And then my y values, I'm hitting all the values from -4 to positive infinity. And that's because these graphs here, as x is going to infinity, is shooting off to positive infinity y value. And as x is going to negative infinity, my y value is shooting off to positive infinity. Part C asks, where are the local maximum and minimum occurring and where are their values? So we're looking at some peaks or valleys is sometimes what you might hear it be called of this graph. And so in here, I see that I have a point here at -8, -4. So that there is a minimum value. It's decreasing and then goes to increasing. And so where are the local maximum and minimum and what are their values? So the minimum value is -4 and it's occurring when x is -8. So again, at the point -8, -4. We also have a minimum value here at 0, 0. A minimum value here at 5, 0. For maximum values, I have a point here. X is -2. The maximum value is 6. We have a value here at 210. So notice that those are points where above, when we were looking at those were interval notation. And so interval notation sometimes looks like points. But look down here, they're not. Those are the X values that we're using. Except in this interval notation, when we're talking about range, range is the only time really we talk about Y values as part of that interval notation. So looking now at where is f of x greater than 0? So we're looking at where is this graph? What are the x values that fall, make the graph fall above the x-axis? And so looking at my x-axis, I'm looking at the y values where it's above. And so looking at my x-intercepts, I can see that it's above between -infinity . Oops, that's a pencil. That's why I'm having so much problem. So -infinity to -8, union -5 to 0. It doesn't have the equal to part on my inequality, so I'm not including my x-intercepts. Then it's above the x-axis from 0 to 5, union 5 to infinity. If this had the equal to part of the inequality, then I would have included all the values from -5 and to infinity, as well as my -infinity to -8. The next question on this exam said, from what we learned in this class, what can you tell me about the polynomial? The degree, the leading coefficient, multiplicity of the zeros, and behaviors. Justify your answer. So I'm not going to write these things down, but I'll explain them. So what do I know about the degree? So we know that the maximum or the degree has to deal with the number of turns there are in the graph. And so looking at the number of turns, so where we're changing from increasing to decreasing or decreasing to increasing. So right here, we're going from decreasing to increasing. There's one change. Here from increasing to decreasing, there's another change. Decreasing to increasing, another change, change, change. So we have 1, 2, 3, 4, 5 changes. So the maximum degree that this polynomial can be is n-1. So n being the number of terms. So 5 minus 1. So the maximum this could be is a degree 4. So this is degree 4 or less. The leading coefficient, well, I could talk about the leading coefficient and talking about the degree by looking at the end behaviors of this graph. So if our end behaviors of the graph are both going in the same directions, which in this case, this is, as x is going to positive infinity, y is going to positive infinity, same thing as x is going to negative infinity, y is going to positive infinity. So I know that my degree is even, which matches up with this is degree 4 or less. And then the leading coefficient has to be a positive number. Think of it, I'm taking a positive number, multiplying it by a positive number. Positive number raised to a power is positive. A negative number raised to an even power is positive times that positive coefficient in front. The multiplicity of the zeros. So we know that the multiplicity of the zeros, when we're crossing the x-axis, that multiplicity is going to be odd. If we're touching the x-axis at that x-intercept, then the multiplicity is even. And so looking at our x-intercepts, the first one going from left to right, we have at x equals -10. This is crossing, so it has to be an odd degree. So let's say that it's a degree 1. Here it crosses at x equals -5. So let's say it's degree 1. It could be degree 3 or 5. Well, not 5 because we know that the maximum degree was 4. So right here it's touching. So the minimum that multiplicity could be would be 2. And then over here we are also touching. So that is 2. So then I'm thinking that maybe I was off. So this was 1, 2, 3, 4, 5. And so maybe that formula was n plus 1. Because if I sum this, this is degree 6. So looking up the definition, or not definition, but the rule, it says a polynomial of degree n can have up to n-1 turning points. So that means if we're looking at the number of turning points, then the maximum degree would be n plus 1. So when I was going through this, I could tell that something was wrong in my way of thinking. And so I needed to go back and kind of look at where I was wrong. And so you'll see sometimes I make mistakes, but a lot of times when I make mistakes, as I'm working through the problem, I can tell that a mistake was made, like I did in this case. So I think my mistakes are sometimes, and hopefully they are learning experiences for you. And that's why I'm just gonna keep that in here instead of going and cutting this out. So let's continue on. We talked about the multiplicities of our zeros. We counted it up, and with those multiplicities, this could be a degree 6. The degree 6 matches with our end behaviors of our graph. And we talked about the end behaviors of a graph as we were looking at the coefficient, leading coefficient. So we've justified our answers and what we just talked about. So let's move on to the next question. The next question says, let f of x equal x to the 4th minus 5x cubed plus 10x squared minus 20x plus 24. And we want to answer the following questions. So using the rational zero theorem, what are the possible rational zeros of f of x? So we can use the rational zero theorem here. We're looking at the coefficients, which in this case is 24. Our values that are factors of our coefficients are plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. So these are all numbers that go into our constant evenly. And now we're going to look at our values of q. Q are factors that divide into our leading coefficient, which is 1 here. So the rational zero theorem says that if we have a polynomial and we have rational zeros, then those rational zeros would have to be in the form of p divided by q. And so looking at this, we had our p-value divided by our q-value. Well, anything divided by 1 is that anything, and so we get back our p-values. So plus or minus. I'm just going to put plus, which is equal to p. So let's find the zeros of the polynomial. So if we plug the value back in, we want to get back 0. So the plugging in those values for x, we can test this by using synthetic division. So let's look at plugging in 1 here. So plugging in 1, looking at our coefficients and writing it down for synthetic division, we're putting in a placeholder of 0 if there's any terms missing. Looking at this, there's no terms missing. Making sure that our terms are in descending order of powers, which they are. And so we have 1, -5, 10, -20, 24. Bringing down our first coefficient of 1, we're multiplying by the number in our box. So 1 times 1 is 1, and we're putting this underneath the next number. -5 plus 1 is -4. 1 times -4 is -4. Summing this 10 minus 4, which gives me 6. 1 times 6 is 6. -20 plus 6 is -14. -14 times 1 is -14. Plus 24, which gives me 10. It's not 0. My remainder is not 0. So this is not a 0 of this polynomial. Looking at this, I'm also trying to be aware of Descartes' rule of signs. Actually, I could have, but I'm actually thinking of the upper and lower bound theorem is what I meant to say. And if this was an upper bound one, then my bottom row would have been all positive numbers, which it's not. So this is not an upper bound. So I'm going to go to my next number 2. I'm going to try that. Writing down my coefficients. Again, 1, -5, 10, -20, 24. I'm going to continue. Bring down my 1. 1 times 2 is 2. -5 plus 2 is -3, 2 times -3 is -6, 10 minus 6 is 4, 2 times 4 is 8, -20 plus 8 is -12, and -12 times 2 is -24. So I get a 0 here. I know then that x equals 2 is a 0 of my polynomial. If x equals 2 is a 0, then I can see what my factor is by subtracting 2 on both sides. So x minus 2 is a factor. Also looking at this bottom row, this is my another factor. It was my quotient if I had done long division. I start 1 degree less than what I was dividing by, which is a degree 4. So this is going to be 1x cubed minus 3x squared plus 4x minus 12. I can continue and go through and use synthetic division to find my zeros of this polynomial, which was my quotient, or I can use other tools. And looking at this, I can see that I can use factoring by grouping. And so if you have 4 terms, sometimes factoring by grouping is helpful. And so looking at my first 2 terms, x cubed minus 3x squared, they both have an x squared in common. I'm going to factor that out of both of those terms. Pulling an x squared out of x cubed, I'm left with x. And pulling an x squared out of -3x squared, I'm left with a -3. And then I'm looking at my last 2 terms, 4x minus 12, and I see that there's a 4 in common with my 4x minus 12, so I'm going to pull out a positive 4, so putting plus 4 here, and pulling out a positive 4, I'm left with x minus 3. And so notice what's inside our parentheses here, x minus 3 is the same in both cases, so I'm pulling that out, leaving me with a x squared. And then if I pull my x minus 3 out of that last grouping, I'm left with a plus 4. So x minus 2 is a factor, but we also see that x minus 3 is a factor. I wanted to see here x squared plus 4. I want to know, when is this equal to 0? I can use my square root method that we learned earlier in this class by isolating the perfect square, which is x squared in this case, by subtracting 4 on both sides and then taking the square root of both sides. When you're taking the square root of both sides, when you're solving an equation, then you need to put this plus or minus in front of the radical. So I look at x equals plus or minus the square root of -4. So this would be x is equal to plus or minus the square root of -1 is I, and so the square root of -4 is plus or minus 2i. So we have our zeros. X equals 2, x equals plus or minus 2i. We saw that x minus 3 here is a factor, and x minus 3 is equal to 0 when x is 3. So here are our zeros of that polynomial. So the next piece of the question asked us to rewrite the f of x as a product of linear and or irreducible quadratic factors. Our irreducible quadratic factors are the factors where they're quadratic and they don't have real numbers as solutions. And we saw that x equals plus or minus 2i for the quadratic factor of x squared plus 4. So we're going to leave that as a quadratic factor. Our f of x value then is equal to x minus 2 all times x minus 3 all times x squared plus 4. The last piece we want to find when f of x is greater than 0. This is a non-linear inequality, and so we wanted to find our critical values, which we did, the values where it's crossing the x-axis, which was at 2 and at 3. And now we want to test our values into our function to see if it's falling above or below the x-axis on each side of our x-intercepts, 2 and 3. And so choose a test value, something less than 2. So let's plug in x equals 0. If we go back into our function and plug in 0 wherever we see an x, we get 0 minus 2, which is -2. All times 0 minus 3, which is -3. All times 0 squared plus 4, which is 4. I'm just wanting to know, is this value greater than 0 or less than 0? And I can see a negative times a negative is positive, times a positive is positive. So this is greater than 0. This is above the x-axis. So negative infinity to 2 is part of our solution. Now choose a number between 2 and 3. So how about x equals 2.5? So if we plug in 2.5 here, we get a 2.5 minus 2 is positive. 2.5 minus 3, that's a negative. And 2.5 squared plus 4 is a positive number. Multiplying a positive times a negative times a positive is a negative number, so that's less than 0. This is below the x-axis. It's a negative number. So one other number to try. So how about x equals 4? It has to be bigger than 3. And so let's go back in again and plug in our numbers into our function. When x is 4, 4 minus 2 is a positive number. 4 minus 3 is positive. 4 squared plus 4 is also positive. Positive times positive times positive is positive. It's bigger than 0. And so our solution is negative infinity to 2, not including 2, so that I have a parentheses there. And then from 3 to infinity, not including 3, so I have a parentheses there. Question number 3 says, graph the following rational function. Make sure the graph the asymptotes and find the intercepts. And so looking at f of x equals x squared plus 4x plus 4 all over x squared plus x minus 2, we want to find the domain of this function. And so let's first start out by factoring both our numerator and denominator. Since we have a rational function, we're worried about values which are going to set our denominator equal to 0. It's going to help me later on if I also factor my numerator, so we're going to go ahead and do that at the same time. And so looking at this, it's a quadratic. My coefficient in front of the x squared is 1, so I'm just looking at what multiplies to be my constant 4 and adds to be my coefficient in front of x here, 4. So it multiplies to 4, it adds to 4 is 2 and 2, so I'm going to factor this as x plus 2 times x plus 2. So the next piece here, we have minus. So what multiplies to negative 2, it adds to positive 1. So this is going to give me x plus 2, x minus 1. So looking at this, x cannot be negative 2, and x can't be 1. Those set my denominator equal to 0. So my domain are x such that x is not those two numbers. Find the vertical asymptotes and points of holes in the graph if they exist. So vertical asymptotes occur at values which set our denominator equal to 0, but it can't set our numerator equal to 0. Or if we cancel like factors, it's not going to leave a value which sets our denominator equal to 0. If it's a hole. If it's an asymptote, which we have just one here because the x plus 2's cancel. What's left, which setting my denominator equals 0, is 1. So we have a vertical asymptote at x equals 1. The hole, though, is occurring at the value which they had like factors, so at x equals negative 2. And I can find out what that value is where the hole is. I know my x value. So to find my y value where the hole is, I'm going to go back in and plug in negative 2 wherever I see an x in this simplified form. So going in there, plugging in negative 2 wherever I see an x, I have negative 2 plus 2 all over negative 2 minus 1. Well, negative 2 plus 2 is 0, all over negative 2 minus 1, which is negative 3. So 0 over a number other than 0 is 0. And so my y value is 0 when x is negative 2. So my hole is at negative 2, 0. To find my y-intercept, this is when my y value, y-intercept is when my x value is 0. So I'm going to let x equals 0. Going in here and plugging in 0 wherever I see an x. I'm left with 4 in my numerator, all over negative 2 in my denominator, which gets me back negative 2. So I have a point at 0, negative 2. My x-intercept is when my y value is 0, or f of x is 0. So we have 0 is equal to technically, I can look at the reduced form, so x plus 2, all over my denominator, x minus 1. But if I multiply both sides by my x minus 1 to clear my fraction, which we were solving for rational function, rational equations at the beginning of the semester. And so here's an example where we're using it later on. So it's testing multiple things that we've learned in this course. So we have 0 is equal to x plus 2. And so this is when x is equal to negative 2. But if you look back at our domain, x cannot be negative 2. And so, and we saw up here that this was our hole. And so technically, there are no x-intercepts. Because x equals -2 is not in our domain. So now looking at finding any horizontal or slant asymptotes if they exist. Looking at our function, we can tell if we have horizontal asymptotes depending on the degree of our numerator and denominator. If our degrees are the same, then it's the leading coefficient of the numerator, which in this case is 1, divided by the leading coefficient of the denominator, which again in this case is 1. And so we have a horizontal asymptote here at y is equal to 1. So let's go in and plot what we know. We just found that we had a horizontal asymptote at y equals 1. So let's just plot that with a dotted line. Even though it's not on the graph, it helps us graph it. We saw that we had a vertical asymptote up here at x equals 1. Actually, yeah, at x equals 1. And so let's do a dotted line at x equals 1. We didn't have any x-intercept, but we had a y-intercept at -2. So knowing where, and I know that I have a hole at -2, 0. And so knowing this and where my asymptotes are on the left-hand side of x equals -1, I can tell what my graph is going to look like. Which looks like this. So now I just need to see what's happening on the other side of x equals 1. Knowing that I don't have any x-intercepts, my guess is that my graph is going to look like this. But I can test just one point, so a value of x bigger than 1. So let's say x equals 2. Let's plug it in, show that it's above the x-axis, and if so, then by what my graph looks like. Or where my asymptotes are, I would know that my graph looks like that. And so going back up to my equation, plugging in 2 wherever I see an x, I'm going to plug it in my simplified form. So I would have 2 plus 2, which is 4. 4 divided by 2 minus 1, which is 1. So 4 divided by 1 is 4. So I have a point at x equals 2, y is 4, which is right here. So we were able to graph our function, our rational function, and then I wanted to know for part F, does the graph cross the horizontal or slant and or vertical asymptote, y or y not? Well, a graph will never cross a vertical asymptote, and that's because it's undefined at that value, and so that value, it's not in our domain. It is possible to cross a slant or a horizontal asymptote. And so what we want to do is we want to set our equation of our asymptote, which in this case is y equals 1. So let our f of x value equal 1 equal our equation. And technically, I can use my simplified form of my equation. So I have 1 is equal to x plus 2 all over x minus 1. If I multiply both sides by my denominator, x minus 1, and solve for x, well, 1 times x minus 1 is x minus 1 is equal to, well, my x minus 1 cancel, x plus 2. Once I try to get x to one side of the equation, notice when I'm subtracting x on both sides, I get here that -1 is equal to 2. Well, that's not true. That's false. And so since we get a contradiction here, we can say that it does not cross the horizontal asymptote. So our next question is write the quantity, the natural log of x squared times y times the cubed root of z all over e squared using sums and differences of simpler logarithmic expressions. Express the answer so that the logarithms of product quotients and powers and radicals do not appear. So recall that if we have multiplication within our argument, that there's which there is in our numerator, then we can rewrite that with addition in between the logs of that product. If we have division, which we do, then we can rewrite it with subtraction. And so we have the natural log of our numerator, x squared times y times the cubed root of z. I'm going to rewrite the cubed root of z as z to the 1/3 power minus, because of the division, the natural log of e squared. So now let's break down the multiplication in between. Multiplication means addition, so I have the natural log of x squared plus the natural log of y plus the natural log of z to the 1/3 minus the natural log of e squared. So now I'm going to use the rule of logs that says I can bring my power of my argument down front. And so the natural log of x squared is the same thing as the 2 natural log of x plus the natural log of y, plus I can bring my 1/3 power down, which gives me 1/3 times the natural log of z, minus, well, the natural log of e squared. Natural log is the same thing as log base e. So log base e of e squared. So e, or base, can I raise e to get back my argument e squared? Well, I can raise e to the 2nd power to get e squared. So the natural log of e squared is just 2. So we have simplified this as a product of simpler logs. The next question says, find the fraction that is equal to 0.1212121212. My hint to you guys, and I saw that some students did this in a different way, but I'm going to, because we were doing sequences in series, I'm going to do it the way that my hint told us. The hint says, think about rewriting this number as a sum of finite terms of a certain sequence. Well, let's rewrite this. This is the same thing as 0.12 plus 0.0012 plus 0.000012. And I can keep on going on like this forever. And so we want to rewrite this. We know what our first term is. That is going to be 0.12. Let's show this is a geometric sequence. And so let's figure out what R is. So if we take a term in our sequence, 0.012, and divide it by the term right in front of it, 0.12, let's simplify this by getting rid of one too many zeros. Actually, I need 4 zeros. That was right. So multiplying through by 10,000. That's going to move my decimal place over 4 times, which means I need to add 2 zeros. So this is equal to 12 over 12,000. They both have 12 in common. And so this is going to give me 1 over 1,000. So my R value is 1 over 1,000 or 1,000ths. And so knowing this, our R value is less than 1. And this is an infinite sum. And so this geometric series is convergent. And so looking at this, let's look at the formula for that summation. When we were dividing here, added 1 extra 0, so this is actually 1 over 100, which is 100ths, which is still less than 1. The formula is a sub 1, which is 0.12, all over 1 minus r, so 1 minus 0.01. So this is 0.12 all over 0.99. Again, let's clear our decimal within our fraction. So if we multiply both numerator and denominator by 100, so multiplying by a fancy 1, we have 12 over 99. Let's reduce that down. They both have 3 in common, so 3 goes into 12 4 times, and 3 goes into 99 33 times. And so we have 4 divided by 33 should give us that fraction of 0.1212, where 1, 2 is repeating itself infinitely. And checking it, it works. Okay, so next problem here. Put the equation of the conic section in standard form and graph the equation. If it's an ellipse, finds the center, foci, major and minor vertices. If the equation is a hyperbola, we're going to find the vertices of the transverse axis, the center, and graph the asymptotes. Okay, so looking, and then if it's a parabola, we're going to find the vertex, foci, and directrix. So looking at my first equation, x squared plus 2x plus y squared minus 8 equals 0. I can see that both of my coefficients in front of x squared and y squared are the same. So that clues me in that I have a circle here. I want to put it in the form that I have x minus h quantity squared plus y minus k quantity squared is equal to r squared. And in this form, I can tell what the center is, which is HK, and my radius, which is R. So I want to complete the square on my X terms. So I have X squared plus 2X. So I'm looking for the same number. And if I may divide my middle term or my coefficient 2 by 2, I have 1. 1 plus 1 is 2. But now I need to think of 1 times 1, which is 1. I'm going to add this 1 to both sides of the equation. So let's not forget to add it over here. I'm going to add 8 to both sides. So this is plus 8, but I added 1 over here. So I also have to add 1 over here. Looking at this x squared plus 2x plus 1 is a perfect square now. And I can rewrite this as x plus 1 quantity squared. Then I have this plus y squared. This is equal to 9. So I have a center here at -1, 0. And my radius is r squared. R squared is 9, so my radius is 3. So looking at x equals -1, y is 0. I have my center here at -1, 0. My radius is 3, so I'm going to go up 3, down 3, left and right 3 from my center. And I get my circle. The next equation is y squared equals x plus 2. Looking at this, I only have the variable y that is squared and not x, so this tells me that I have a parabola. Parabolas, we saw the form y minus k quantity squared equals 4p all times x minus h. This is actually in this form. We can see that our vertex is at hk. So our vertex here is our x value is -2 and my y value is 0. So I have a vertex here at -2, 0. It's my y value that's squared, so I know that my parabola shape is facing left or right. My coefficient in front of this x plus 2, that is 1. So my 4p equals 1. P is positive, it's 1/4. So I know that my parabola shape is going towards the positive x direction. I can find my y-intercepts really easily by letting x equals 0. And so I would get y is equal to 0 plus 2, or y squared. And then taking the square root of both sides, I get y equals plus or minus √2, which is about 1.7 and negative 1.7. So I found my vertex. I found my y-intercepts and my x-intercept. My foci is 1/4, so I would add 1/4 to my x value. So -2 plus 1/4. So I have a focus at the point -1.750. And then it asks for the directrix. This would be the line x equals. So from my vertex, I'm going to add 1/4. Actually, it's not x. In this case, it's y equals. No, it's away from it. It's x equals. Well, I'll get it right. X equals. And I'm adding 1/4 to my x value, which is -2, and then actually subtracting it. So it's going to be -2.25. So part C wants to know, solve the linear equation, solve the nonlinear system of equations, and find the points of intersections if they occur. And so that nonlinear system equation is what we just looked at, those two conic sections. And there's a couple ways that we can approach this. Well, I noticed that if I sum this one equation plus the negative of this other equation, so if I multiply this one by -1, that would give me a negative x squared minus, let's actually get everything to one side of the equation, just like the other one. So first equation, I'm going to have this x squared plus 2x plus y squared minus 8 equals 0. This other one, I'm going to have y squared minus x minus 2 equals 0. But I'm going to want to add the equations together and get rid of that y squared value. And so let's multiply this through by -1 and put that underneath. I'm going to put it in the order that they occur. So I don't have an x squared, but multiplying this by -1, I would have a plus x minus a y squared plus 2 equals 0. Summing these together, I have x squared. 2x plus 1x gives me plus 3x. Y squared minus y squared cancels, and I have negative 8 plus 2, which gives me minus 6 equals 0. And so I want to solve here for x. I notice that this does not factor nicely, and so I'm going to use the quadratic formula. So x is equal to negative b, negative 3, plus or minus the square root of b squared, which is 9, minus 4 times a, which is 1. Negative 4 times 1 is negative 4, times negative 6 is plus 25, all over 2 times a, which is 2. So I get negative 3 plus or minus the square root of 34 all over 2. So that's my x value. Okay, so I need to be careful. Going back and checking my work and plugging this into the calculator, making sure I didn't do anything wrong. I noticed that when I noticed when I was multiplying to get what the radicand was, what was underneath the radical, I did that wrong. So right here, negative 3 plus or minus the square root of b squared, so 9, minus 4 times a times c. So negative 4 times 1 times negative 6. It's going to give me plus 24 all over 2a, so all over 2. So this is x is approximately, so I went and I plugged this into decimals. So negative 3 actually plus or minus the square root of 33 all over 2. And we get back that x is approximately 1.37. And then if I plug in that minus in between, I get x is negative 4.37. So not great numbers, and those are approximate. To find our y value, we want to plug those in. So if I had y squared is equal to x plus 2, I would have y squared is equal to 1.37 plus 2, which is 1.37 plus 2 is 3.37. So y is equal to plus or minus square root of 3.37. So doing the same thing, we would look at this negative 4.37. We would have y squared equals negative 4.37 plus 2. I can see I'm going to have some problem because I'm going to have a negative number here, negative 2.37. And when I take the square root of both sides, it's not a real number. So my solutions look like it's 1.37 plus or minus the square root of 3.37. Let me look at what that is. Which is approximately 1.835. And then I pulled this up on Desmos, so let me just bring this over and show you the graph. So we got our circle, we got our sideways parabola, and we have our solutions we just found. So looking at the next part, determine the partial fraction decomposition of the following. We have 6x squared minus x plus 3 all over x cubed minus x squared plus x minus 1. So we're looking at this. Let's factor that denominator. So let me rewrite my numerator. I have 6x squared minus x plus 3 all divided by. So I notice here that I can factor by grouping. I can pull out an x squared. If I pull out an x squared from those first two terms, I'm left with x minus 1 plus, well, those last two terms are x minus 1. So now let's factor out the x minus 1. We're going to have x squared plus 1. That's not reducible over the real numbers. So we have it factored as x minus 1 all times x squared plus 1. Now when we rewrite this for partial fraction decomposition, it depends on if we have linear factors and or quadratic factors and how we're going to write it. And if that linear factor or quadratic factor is repeating. They're not repeating, so we have a all over x minus 1 plus, this is quadratic, and so we have bx plus c all over our quadratic irreducible x squared plus 1. So now looking at this, we can clear our fractions by multiplying both sides by our LCD. Use common denominator, which in this case is x minus 1 all times x squared plus 1. When we do that to both sides, so I'm just gonna actually do this. So it's like we're multiplying on both sides. We're just going to be left with a numerator on the left-hand side, 6x squared minus x plus 3 is equal to our a value. Distributing this, the x minus 1 is going to cancel, leaving us with x squared plus 1. Plus, we're going to have our numerator bx plus c. But when we distribute this to the second grouping on the right-hand side, x squared plus 1 cancels, leaving us with a factor of x minus 1. So now let's distribute on the right-hand side, distributing our a. We have a times x squared plus a times 1 is a, plus over here we have bx times x, so that's bx squared. Bx times negative 1 is minus bx. C times x, so plus cx. C times negative 1 is minus c. So now looking at this, our coefficient in front of the x squared is 6. So I have 6 here is equal to, now looking at the coefficients in front of the x squared on the other side, we have ax squared plus bx squared. So that 6 must equal a plus b. Now looking at our coefficient of minus x, there's a negative 1 here. This must equal, over here we have a minus bx plus a cx, so it must equal negative b plus c. And then our constant 3 must equal our constants on the other side, which are a minus c. So we have a system of equations, 3 unknowns, 3 variables. It's said to use matrices in here to solve for this. And so when we write our matrix, I'm looking at my column A, then I'm going to have column B of my coefficients C, and then my constants. So I have A, 1, B is 1, there's no C value, so 0 equals 6. My next row is 0, negative 1, 1, negative 1. My last row is 1, 0, negative 1, 3. And so now looking at this, my first row, first column, I want a 1 where I have it. I'm going to use this row here to get rid of the entries below. And I already have a 0 below on the second row, first column. I want a 1 in the third row, first column. So I'm going to look at negative row 1 plus row 3. So I tend to like to write the rows down that I'm not changing, and then change the one I'm going to change. So negative 1 times 1, the first row, plus the third row. Negative 1 times 1 is negative 1 plus 1 is 0. I have a negative 1 plus 0 is negative 1. 0 times negative 1 is 0 plus negative 1 is negative 1. Negative 1 times 6 is negative 6 plus 3 is negative 3. So now I'm going to go into changing the second column. In the second column, I want this entry of negative 1 to be a 1. So I can look at negative row 2. So that would keep all my other entries the same in the first row and the third row. I'm just changing row 2, multiplying that through by negative 1. I have negative 1 times 0 is 0, negative 1 times negative 1 is 1, negative 1 times 1 is negative 1, and negative 1 times negative 1 is 1. So now I'm going to get rid of the one above that leading 1 and below that leading 1 in the second column. And so I can do that by negative row 2 plus row 1. So I have 1, 0, 1, 5. Now if I look at row 2 plus row 3. Sorry, I'm trying to write on a different program here, so it's not as nice. Okay, so row 2 plus row 3, I have 0 plus 0 is 0. 1 minus 1 is 0. Negative 1 minus 1 is negative 2. And 6 plus, no, 1 plus 3 is 4. So looking at this, I can see, I can read this off, that last row, I have negative 2c equals 4. So divide both sides by negative 2, I get c equals negative 2. This other row right here is b minus c equals 1. But if c is negative 2, I would have b minus a negative 2 equals 1. So b plus 2 equals 1. So b is negative 1. This first row, I have a plus c equals 5. Well, we just saw that c is negative 2. So I have a minus 2 equals 5. Adding 2 to both sides, I get a equals 7. So going in here, let's go back. We know what our coefficients are. And so we have here that a, which was 7, all over x minus 1, plus b, which was negative 1, times x plus c, so minus 2, all over x squared plus 1 is equal to our fraction that we started out with. So our next question says list the first 5 terms of the sequence where a sub 1 is 3 and a sub n is equal to 2 times the quantity a sub n minus 1 minus 1. So we know what the first term is of our sequence. So when n is equal to 2, to get our second term, we would have a sub 2, plugging in 2 wherever we see an n, is equal to 2 all times. We're going to have 2 minus 1, which is a sub 1, but a sub 1 is 3, so we have 3 minus 1. So our second term is equal to 2 times 3 minus 1 is 2, so our second term is equal to 4. Our third term we can find by going in and plugging in 3 wherever we see an n. If I plug in 3 where I see an n, I have 2 all times a sub 3 minus 1 is a sub 2, but a sub 2, it gives me 4. So I have a recursive sequence. A sub 3 is 2 times 4 minus 1. 4 minus 1 is 3, so a sub 3 is 2 times 3, which is 6. So a sub 4, plugging in 4 wherever I see an n, I have 2 times, well, a sub 4 minus 1 is a sub 3, which is 6 minus 1. So this is 2 times 6 minus 1, which is 5. 2 times 5 gives us 10. Last term, a sub 5 is 2 times a sub 5 minus 1 is a sub 4, but a sub 4 we just found was 10. 10 minus 1. So we have 2 times 9, which is 18. So I get a sub 5 is 18. So our first 5 terms of our sequence is 2, 6, 10, and 18. So the next part says for the sequence, -3, 1, -1/3, 1/9, answer the following question. Is this an arithmetic, geometric, or geometric sequence, or neither? Explain how you came up with this answer. So looking at this, I can tell what my first term is. A sub 1 is -3. If it is geometric, then if we take a term divided by the term right before it, this is always going to give us the same constant r. And so if I look at the second term divided by the first term, I get -1/3. If I look at the third term divided by the second term, so -1/3 divided by 1 is also -1/3. If I look at the fourth term divided by the third term, I have 1/9 divided by -1/3. Fraction, division, invert, multiply. So 1/9 times -3/1, which is -1/3. And so looking at this, if I take a term, divide by the term right before it, we get always the same constant r, which is -1/3. Okay, so I explained why it is geometric. What is the formula? Well, a sub n for geometric is equal to the first term, which is -3, all times r, which is -1/3, raised to the n minus 1 power. That was one of those formulas. What is the sum of this? Well, our r value is -1/3. The absolute value of r, which is the absolute value of -1/3, is less than 1. And so therefore, this is convergent, which means if I summed all of these terms, it's going to equal a number. And that number that it is equal to is the first term, which is -3, all over 1 minus r, which is -1/3. So I have -3 all over. I have a 3/3 plus a 1/3. 3/3 plus 1/3 is 4/3. Fraction divided by a fraction, or not a fraction divided by a fraction. But we have -3 divided by 4/3, so times the reciprocal 3/4. And so this is going to give me back -9/4. Several logs are stored in a pile with 36 logs on the bottom layer, 35 on the second layer, 34 on the third layer, and so on. So we have 40. There's a typo there. No one caught that and said anything in class. So this should have been in here, according to what this was saying. 40. Down here, 39, 38. Well, it's actually, it really depends on what you decided to do, because no one said anything to me. In the other class, theirs was this one. I was just trying to change the numbers for this version, which didn't do a good job. So let's change it to this. So technically I'm looking at 36 plus 35 plus 34 plus ... plus 1. I notice that this is an arithmetic sequence because technically I'm subtracting 1 from a term to get to the next term. And so my common difference here is -1. My first term of the sequence is 36. And so one of the formulas for an arithmetic sequence is that we're looking at the nth term is equal to the first term plus the quantity n minus 1, that quantity times d. So I have a sub n is equal to the first term, which is 36, plus n minus 1. -1 minus 1 is -2. Oops, n minus 1, not d minus 1. So negative n minus 1 times d, which is -1. So let's distribute that -1. So 36, -1 times n is -n, -1 times -1 is +1. So we have a sub n is equal to 37 minus n. So now let's look at the formula for a summation of a arithmetic sequence. So technically we did all this work and we really didn't need all of this, what the formula or what the nth term formula was to get the summation. The summation says that S of n, the summation is equal to n, what we're summing to, all times a sub 1, the first term plus the last term, a sub n, all over 2. Well, n, we're summing actually, we need to figure out what n is, how many sum we're doing. Well, in this case, we have up to 36. So if I'm starting at what? Oh, well, I know n is 36 then. So I have 36 all times the first term, which is 36, plus the last term, which is 1, all over 2. So doing this, we get 36 times 37, but 2 goes into 36 8 times, so we really have 18 times 37. which is 666 logs in our pile. Okay, so there was an extra credit problem, but it's getting late and I've been working since 7:45 in the morning and it's 11:05. So I'm going to stop there. That is the key to this exam. Hopefully that was helpful for my students and anybody else who happens to be watching.